Okay, so here we have this cylinder and we have this ball rotating around, and it's getting slowly closer to the middle until it reaches its second point. So we have, what I wrote down is that you have, mass times acceleration tangential, mass times acceleration radial, and you also have this gravitational force. So what you realize here is that you have this angle theta. So the gravitational force as a component in this direction is the same as, if I say MAR sine theta, that's the same direction as G. So you can kind of say like, oh, it's equal to G, right? So what you have is you have the component of radial acceleration caused by gravity is actually mg, gm, whatever, is actually the secant of theta times mg. So here we have the component of radial acceleration that's caused by gravity. So we're going to say we're just going to only use this now. We're not going to go back to this when we're talking about this. What we also have is we have a acceleration, an outward acceleration, because what this thing wants to do is just keep going this way. And there's a component of this, as you can see, that is in the direction away from the center. And what that's called is I forgot, but what it is it's v squared divided by r, and I think it's acceleration. I don't remember, but it's some kind of acceleration that is away from the center. So if you want to find the mass times acceleration in the radial direction, what you have is you have negative secant theta mg, that is pulling in, and then you're adding v initial squared, or v tangential squared, divided by r. So what this is tangential velocity squared divided by r is this outward. So you have this is going out away from the center, this is going into the center. So if you want to find acceleration in the radial direction, and you can include, like you could even include like a frictional force that is stopping it from rolling down, or something like that. But that's also stopping, it's acting on both. The friction is acting on both the outward acceleration and the gravity acceleration equally. Right, so it has an equal component that is resisting both components of acceleration. So the frictional force that is affecting the tendency to want to go away from the center of the circle is also affecting the gravity pulling it down. So what you would have is you have a frictional force resisting here, you have a frictional force resisting here, and they're equal and opposite, so they're zero. Right, so the acceleration in the radial is just negative secant theta g plus tangential velocity squared divided by the mass, because we're just dividing mass over here. So what we want to do next is we want to set up our we have a distance in the radial direction is acceleration radial squared times t squared, over 2 plus the velocity in the radial initial times t plus the initial position. So the initial velocity in the radial direction is this tangential velocity. Okay. So we also have distance is tangential, so we have acceleration tangential times g squared over 2, and there isn't a tangential acceleration other than friction. Right, so what we can say is acceleration tangential is equal to the initial minus mu kg, where we're dividing m by both sides. So this would be mu k normal force, and this would be mass acceleration, but we're dividing out mass, so it's just mu kg. So now we have tangential as initial acceleration minus mu kg. So we have velocity tangential initial, which we have up here, and then this Sorry, I messed up. This is not the same as up here. I misspoke. Ignore what I said about that. This velocity is not the same velocity that's up here. So this acceleration is what's up here. This velocity has nothing to do, there's no extra velocity flying away. It's an acceleration. All right, so what we have here is we have a second position, the initial position here. So what we need to do is we need to solve for time from here, because we know the initial position, which is r equals something, and then we know the final position, which is r equals something else. So these things become knowns. So let's just say that this is 1. And what we have now is we have ax squared plus bx plus c, which is quadratic formula. So it's like negative b plus or minus the square root of b squared minus 4ac divided by 2a. So now t is known. So t is known. Okay, so we plug t in over here. And we can solve for the position that the object has traveled in the tangential direction, and then we can see exactly where it finishes. Right? And what we can also do is we can do this differently, where we can time how long it takes to reach the bottom, and then we can solve for the angle of the cone. So that's another way we can do it, because we can have a starting, finishing position in terms of how far it's traveling in the radial direction, and we can use that to solve for the angle. Because we know the time, we know the positions, and then the angle here is a function of the radial acceleration, which is right here. So you kind of have a lot of things that you can do with this, just in terms of your kind of basic physics and